Hello everyone. Today we talk about Cauchy residue theorem. So first we will discuss the statement of Cauchy residue theorem. Let f of z be analytic inside and on a simple closed curve C except at a finite number of isolated singular points z1, z2 and so on zn lying inside C. So before we are, then integral over C f of z dz is equal to 2 pi I summation k is equal to 1 to n residue of f at the singular points zk. So yeah, k is equal to 1 to n. That means residue of sum of the residue of f of z at the singular points. Remember, the contour integral is taken in the anti-clockwise direction. So already I told you anti-clockwise direction means a positive sense. So this is the clockwise. So in this direction we can call it as anti-clockwise direction. So this direction. Okay. So before that we move on to the topic. So what do you mean by isolated singular points? A singular point z is equal to a is called an isolated singularity of the function f of z if there exists a neighborhood of the point A in which there is no other singular point lying in it. So what do you mean by isolated singular point z1, z2? Suppose if we can call it as z1 as an isolated singular point. If I construct a small circle around z1, there is no other singular point containing the neighborhood other than z1. Okay, that point we can call it as isolated singular points. So f of z is analytic on and inside a simple closed curve C except at a finite number of isolated singular points. That means, so z1 is an isolated singular point. If I construct a small circle around z1, this neighborhood should not contain any other singular point other than z1. Similarly, z2, z3, these singular points we can call it as isolated singular points. Then integral over C f of z dz is equal to 2 pi I into sum of the residue of f of z at the singular points. Okay. Now we move on to the evaluation of residue. So the residue of the function f of z at an isolated singularity z is equal to a is the coefficient of z minus a the whole to the power minus 1 in the Lorentz expansion of f of z about z is equal to a. So in Lorentz expansion means already we know the expansion of Lorentz series f of z is equal to summation n is equal to 0 to infinity a n z minus a the whole to the power n plus summation n is equal to 1 to infinity b n divided by z minus a the whole to the power n. So this expansion contains positive as well as negative powers of z minus a. Remember, Lorentz expansion contains both positive as well as negative powers of z minus a. In this Lorentz expansion, the coefficient, if I expand this, what do you get? A naught z minus 1 plus a1 z minus a the whole to the power 1, a2 z minus a the whole squared and so on. Plus put n is equal to 1, b1 divided by z minus a, b2 divided by z minus a the whole squared and so on. See, the expansion contains positive as well as negative powers of z minus a. In this expansion, coefficient of 1 by z minus a will gives residue of f of z. So coefficient of 1 by z minus a means b1. b1 is the residue of f of z at z is equal to a. This is one way of manipulating residue. So another method is, if the singular points are pole of order 1, if the singular points are pole of order 1, or we can call it a simple pole of f of z, then how we are going to manipulate residue? Residue of f of z at z is equal to a is limit z tends to a z minus a f of z. Okay, second one, If Z is equal to A is a pole of order n, other than simple pole, other than order 1, it is a pole of order n. This is the formula. We can manipulate residue. 1 by n minus 1 factorial, limit Z tends to A, d power n minus 1 divided by d Z power n minus 1, Z minus A the whole to the power n f of Z. Using this, we are going to solve the problem. So first we are going to discuss one problem related to Cauchy residue theorem. Okay, not Cauchy residue theorem. First we can manipulate a residue of the function. Calculate the residue of f of Z is equal to 1 minus e power 2z divided by z cube at Z is equal to 0. So at Z is equal to 0 means first we can manipulate singular point of the function. So singular point means already we know that denominator term will be equal to 0. That means Z cube is equal to 0, Z is equal to 0. So Z is equal to 0 is a singular point of the function f of Z. For this function we can manipulate residue. If it is possible to expand the given function f of Z as a Lorentz series expansion, from the Lorentz series we can easily manipulate residue. So already we know that by the definition of residue, how do you manipulate a residue of the function in the Lorentz expansion? That is the coefficient of 1 by Z minus A. So coefficient of 1 by Z minus A will give the residue of f of Z. So you can expand. Do you know the expansion of e power z? What is e power z? 1 plus x divided by 1 factorial. Sorry, z divided by 1 factorial. Z square divided by 2 factorial. Z cube divided by 3 factorial and so on. Using this, I am going to evaluate e power 2z. In the place of z, you can replace 2z. So 2z the whole square by 2 factorial, 2z the whole cube by 3 factorial and so on. So e power 2z can be written as 1 plus 2z, 4z square, 2 to get cancelled, 2z squared. This is 8z cube, 6. 8 by 6 means 4 2s are 3 2s are 4 by 3 z cube. So from this I can subtract 1 e power 2z from 1. 1 minus e power 2z is, so 1 get cancelled, minus 2z etc. So from this I can expand. F of z is equal to 1 minus e power 2z by z cube. You can replace this quantity by this. So what happened? Minus 2z, minus 2z squared, minus 4 by 3 z cube and so on divided by z cube. In the numerator, one z term will be common, so take it outside. So minus 2z minus 4 by 3 z squared and so on divided by z cube. So 1 z get cancelled. The denominator you have z squared. So minus 2 by z squared, minus 2 by z, minus 4 by 3 and so on. So from this series contains both positive as well as negative powers of z about the origin. So already we know that by the definition of a residue, coefficient of 1 by z, because we talk about z is equal to 0 as a singular pointer. So z minus 0, coefficient of 1 by z minus 0. What is coefficient of 1 by z minus 0? Minus 2. So the residue of the function at z is equal to 0 is minus 2. So from this we can manipulate residue. Okay. So from this expansion contains only finite number of negative powers, only 2 terms. So finite number of negative powers, that singular points we can call it as pole. So only 2 terms it contains. It's a pole of order 2. Z is equal to 0 is a pole of order 2. So from that we can manipulate residue also. So one more problem we are going to discuss by using Cauchy residue theorem. Okay, integral over c z minus 1 divided by z plus 1 the whole square z minus 2 dz, where c is a circle, modulus of z minus I equal to 2. So first we are going to identify the singular points. Singular points means we can equate denominator term is equal to 0. So what about the denominator term? Z plus 1, that is z plus 1 the whole square into z minus 2. Z plus 1 the whole square into z minus 2, that is z plus 1 is equal to 0, z is equal to minus 1 twice, z is equal to 2. So z is equal to minus 1 is a pole of order 2, double pole, or we can call it as pole of order 2, pole of order 2, or we can call it as double pole. Z is equal to 2 is a simple pole or pole of order 1, simple pole, or we can call it as pole of order 1. Okay, so next what we are going to do, among this pole, which one will lies inside C and which one will lies outside C. So what about your C? C is a circle, modulus of z minus I equal to 2. So modulus of z minus I equal to 2 means already we know that modulus of z minus a equal to r, it represents a circle with the center at a comma 0 and radius is r. But what about here z minus I? So center at 0 comma 1 and radius is equal to 2. Center at 0 comma 1 and radius is 2 means how we are going to sketch the diagram. So center at 0 comma 1. So 0 comma 1 means y-axis only we have 0 comma 1. So here 0, 0 comma 1. Center at 0 comma 1. Radius is 2. So from this point 2 unit above, 2 unit below, this is minus 1. From this 2 unit 1, 2. 1, 2. Right side also 1, 2, minus 2. Now you can join all the points. So center at 0 comma 1. So minus 1, obviously minus 1 will lies inside the circle. Z is equal to 2. Z is equal to 2. Suppose we have a doubt. See like this. Okay. You just see the diagram. So Z is equal to 2. It's not inside. So suppose if you have a doubt to sketch the diagram now, so another method will also be there. You can directly substitute the value of z in this region. So put z is equal to minus 1. Minus 1 minus I means square root of minus 1 the whole squared plus minus 1 the whole squared. So root 2. Root 2 value is nothing but 1.73 something. This value is obviously less than 2. Similarly, put z is equal to minus 1. Minus 1 put z is equal to 2. 2 minus I, square root of 4 plus 1, so root 5. Root 5 is 2.13 or something else, more than 2. So obviously this value will be more than 2. So you can sketch a diagram properly. It not touching the line. Sorry. So 2 point something, so it is greater than 2. So z is equal to 2 lies outside. See, therefore, only the pole z is equal to minus 1 lying inside. See, the z is equal to 2 does not lie inside. See, so we can manipulate residue at only those singular points lying inside. See, that also z is equal to minus 1 is a pole of order 2. So we can use the formula. So pole of order 2 means we can apply the formula residue of f of z is equal to 1 divided by n minus 1 factorial limit z tends to a d power n minus 1 divided by d z power n minus 1 z minus a the whole to the power n into f of z. This is the formula. But here order 2 means n is equal to 2. So 2 minus 1 factorial means 1 factorial. Limit z tends to minus 1. Okay, d power 2 minus 1 is d by dz, z plus 1 the whole square, z minus 1 divided by this and this get cancelled. So z tends to minus 1, d by dz, z minus 1 divided by z minus 2. So limit z tends to minus 1, d by dz is into z minus 1 divided by z minus 2. Now you can differentiate this. If I differentiate this, what happened? U by V method. Z minus 2 the whole square, Z minus 2 into 1 minus Z minus 1 into 1. So when you simplify this, you will get minus 2 plus 1 minus 1 divided by Z minus 2 the whole square. So residue of f of z at z is equal to minus 1 is minus 1 divided by minus 1 minus 2 the whole square is minus 1 by 9. Now you can apply it in the formula. So what is the formula? Integral over C f of z dz is equal to 2 pi I into sum of the residue of f of z at the singular points. Here only one singular point lying inside C. So we can manipulate residue at only one point, that is z is equal to minus 1. You can directly substitute the value of z is equal to minus 1, residue of z is equal to minus 1. So 1 by 9, this is equal to minus 2 pi I divided by 9. This is the final answer. So I want to discuss one more problem under residue theorem. Evaluate the integral by using Cauchy residue theorem. Integral over C tan z by 2 divided by z minus 1 minus I the whole square dz, where C is the boundary of the square whose sides are x is equal to plus or minus 2 and y is equal to plus or minus 2. So here I can consider the given integral as I, integral over c tan z by 2. So tan z by 2 can be written as sine by cos. So here I can express sine z by 2 divided by cos z by 2, z minus 1 minus I the whole squared. So first we are going to find out the singular points of the function f of z. This is your f of z. Okay. This is your f of z. So singular points means denominator term will be equal to 0. Denominator means cos z by 2 equal to 0 or z minus 1 minus I the whole square equal to 0. Cos z by 2 equal to 0 means, so for what value of this function, cosine function of this will be equal to 0. Cos 0, 1, cos 90. So pi by 2, okay, 3 pi by 2. Similarly, minus pi by 2, minus 3 pi by 2, 5 pi by 2, etc. So, cos z by 2 equal to 0 implies z by 2 equal to 2n plus 1 pi by 2. If I put n is equal to 0, pi by 2. If I put n is equal to 1, 3 pi by 2. If I put n is equal to minus 1, minus 2 plus 1, minus pi by 2, etc. Okay. So, z is equal to get cancelled. Z is equal to 2n plus 1 into pi, where n belongs to z. Z means integer. And also z minus 1 minus I the whole square equal to 0 means z is equal to 1 plus I is a pole of order 2, because we have two roots. Z minus 1 minus 1 repeated 2 times. So z is equal to 1 plus I is a pole of order 2. But what is given in this problem? C is a boundary of the square whose sides are x is equal to plus or minus 2 and y is equal to plus or minus 2. See, how do you sketch the diagram? X is equal to plus or minus 2. This is equation of x-axis. We can call it as y is equal to 0. Y is equal to minus 2. It's a line parallel to. Okay. So this is y is equal to minus 2. Similarly, 2 units above. Y is equal to 2. Similarly, x is equal to minus 2 here. X is equal to 2 here. So this is x is equal to minus 2. This is x is equal to 2. See. Sorry. So like this we can sketch the diagram. Okay. After this we are going to analyze whether those singular points which among this which one will lies inside C. So here pi by 2 minus pi by 2. Obviously pi by 2 and minus pi by 2 will lies outside. Sorry. 2 to get cancelled, no? Pi only will lies outside. And what about 1 plus I? 1 comma 1. 1 comma 1 means obviously it lies inside only. So the only one singular points lying inside. See, among this only one. So z equal to plus or minus pi, plus or minus 3 pi and so on will lie outside C. Hence the only singular point lying inside C is z is equal to 1 plus I. That also a pole of order 2. Pole of order 2. So we can find the residue for the singular points. Once again we are going to give the same formula. So that is limit, because pole of order 2 means limit z tends to a 1 by n minus 1 factorial limit z tends to a d power n minus 1 divided by d z power n minus 1 z minus a the whole squared into f of z. You can substitute here, put n is equal to 2. 2 minus 1, 1 factorial. In the place of a you can write 1 plus I. Put n is equal to 1 means 2 minus 1 d by dz. In the place of a 1 plus I, so z minus of 1 plus I the whole squared into f of z. What is your f of z? This is your f of z. Okay. Tan z by 2 divided by, so this and this get cancelled, only tan z. Now differential of tan z is secant squared. With respect to z means 1 by 2. Now you can apply z tends to 1 plus I. So you will get 1 by 2 secant squared 1 plus I divided by 2.